So let us continue our ring exercises now with this one, exercise 16. Now here we have a commutative ring in which we are considering the set of all nilpotent elements. We have already seen in the previous exercise what a nilpotent element is. An element A in a ring is nilpotent if some power of A equals 0, where the exponent is a positive integer. Now we have to show that the set of nilpotent elements in a commutative ring is a subring. So let's see how we can solve this. Let R be a commutative ring. And let N of R denote the set of all nilpotent elements in R. If you want, you can of course use some other symbol to denote this set. N of R I am writing because the N for nilpotent and it's of R. Okay, so now we need to show that this subset is a subring. So the first thing we need to show is that this is a non-empty subset, and in fact we will show that the zero element, because anyway we are going to show that this is a subring, so the zero element in the ring should belong to this subset. Note that, so that means the first thing we are going to note is that the zero element itself is a nilpotent element, which is almost obvious. Zero is a nilpotent element since the first power of 0 is equal to 0. So that's just it, because this exponent 1 is a positive integer. Now next, let A and B be two nilpotent elements. Then there exists smallest positive integers n and m such that the nth power of A equals 0 and the mth power of B equals 0. Of course, some positive integral powers of A and B are equal to 0. So that means there exist some smallest values of these exponents also for which this thing will happen by the well ordering principle. And the smallest nature of n and m will actually be used. So now our aim is to first of all show that the sum A plus B is again in N of R, that is A plus B is also a nilpotent element. In order to show that, we have to prove that some positive integral power of A plus B also equals 0, just like these ones. We have A plus B to the power, okay, let me just write it in the middle, that way I will have space. N plus m minus 1. So we are considering this particular power of A plus B. Note one thing, that because n and m are both positive integers, so n plus m minus 1 is also a positive integer, because in the least possible case where n and m are both equal to 1, still this thing is equal to 1, this exponent. Now, just like our usual binomial expansion that we already know very well, and which works in the system of say real numbers or in the system of complex numbers, also works in any general commutative ring, and the expansion actually is the same. Summation n plus m, first we write the binomial coefficient, say r, n plus m minus 1, choose r. In old notation you also write this as n plus m minus 1 cr, okay, and followed by powers of a and b, a to the power r times b to the power this minus r, but I choose to write another variable, say s, such that the sum of r and s should be this thing. If you decide to not use a new variable and write in place of s n plus m minus 1 minus r, then you have to write the variation of r, that is r varies from 0 to n plus m minus 1. In fact, here also that thing is there, just we have written actually both the expansions, whether you use s or you don't use s as a new variable, are the same thing. If you are still doubtful about this general expansion in the commutative ring, you can look at the smallest non-trivial situation regarding this, namely a plus b whole squared, and its binomial expansion, which is something that we almost know by heart even without knowing anything else. I mean, for the first time when we are introduced to elementary algebra, we memorize this, right? A plus b whole squared equals a squared plus 2ab plus b squared. Now this thing in a general commutative ring is also true. What is a plus b whole square? Is just simply a plus b times a plus b, and keep in mind that now our a and b are just like these a and b in a general commutative ring. So if we multiply the things up using the two distributive laws, then we have, after using both the distributive laws as many times as we want, I mean as we need, we ultimately have this. Now because we are in a commutative ring, AB and BA are equal, and that's why we get 2AB. So the formula is still true in this very general situation, and the other expansions are also similarly true. And one can in fact prove this binomial expansion simply by induction on the exponent. This of course is a special case where the exponent is like this. In general, you can prove the binomial expansion in a general commutative ring. Similarly, just like how you usually do for real and complex numbers. And I want you to do that and see whether what I am saying is true or not. Anyway, we assume that that is true, and we are now going to use this expansion. Okay, now we can use the fact that these exponents n and m are the smallest such for which these powers are 0. Since r plus s is equal to n plus m minus 1, we cannot have r less than n and s less than m simultaneously. Why? What would go wrong if we have both these things true? See, because we are dealing with integers. So if r is less than n and s is less than m, then you also have this thing, r is less than or equal to n minus 1 and s is less than or equal to m minus 1. But then if you add these two inequalities, you get r plus s less than or equal to n plus m minus 2 because of these two minus 1s. But you also have this, so n plus m minus 1 is less than or equal to n plus m minus 2, which is impossible. So this is a contradiction, and that is why at least one of them has to be false. That is, we should have either r greater than or equal to n or s greater than or equal to m or both. So writing the same thing, r is greater than or equal to n or s is greater than or equal to m or both, of course, and hence a to the power r times b to the power s is equal to 0 for all r and s satisfying these conditions. Why? Because if r is greater than or equal to n, then a to the power r can be written as a to the power r minus n plus n, and the rule of exponents in this case, although we are in a ring and the operation is multiplication, it's not necessarily a group, but still those rules of exponents that we know in group theory are true provided the exponents are positive or non-negative actually. So if this happens, then we can write it like this. So using one of those rules of exponents, you get this, and this nth power of a is 0, and so the product, it becomes 0. So that means if this inequality is true, then the rth power of a is 0. Just like that, if this inequality is true, then the sth power of b is 0. That means all these terms are actually equal to 0. Thus, we have this which implies that a plus b is in the set of nilpotent elements, and which is thus closed under addition. Next, showing that the sum is a nilpotent element is somewhat involved. Showing that the product and the negative of an element, that is its additive inverse, is nilpotent, is much easier. So next we see how we can conclude that minus a is also a nilpotent element. we of course consider the nth power of minus a, and in a general ring, not even in only in a commutative ring, this thing, just using the elementary ring properties, equals plus or minus of a to the power n, depending on the parity of n. If n is positive, if n is even, then it is just simply a to the power n, and if n is odd, then this is minus a to the power n. So this becomes plus or minus a to the power n, which of course is 0. So minus a also belongs to this, and thus we have managed to show that this n of R is an additive subgroup, a subgroup of the ring R under addition. To prove that it's a subring, the only thing left for us to show is that AB also is a nilpotent element. Finally, AB to the power, say, we take n plus n. Now here commutativity of the ring multiplication will be used. Because of that commutativity, we have this, and both these powers equals 0, so the product is 0, because again if you use those rules of exponents, the first power equals a to the power n times a to the power n. So a to the power n is 0. Just like that, in that one, b to the power n times b to the power m, that b to the power m is 0. Hence AB belongs to n of R. This shows that n of R is a subring of R. Note that in showing that a plus b is again a nilpotent element, commutativity of the ring has been used in an essential manner. Without commutativity, we cannot say such things. But the solution is now over. Now we can move on to the next one. Next is 17. Show that 0 is the only nilpotent element of an integral domain. Of an integral domain. Let D be an integral domain and let A belonging to D be nilpotent. Keep in mind, do not use this notation simply because you have used it in the previous exercise. It may not be something standard in the mathematical literature, so its use is, it is there, and in that exercise it's over. That's why we have written in words that let this be nilpotent. Okay. Then there exists as, again just like before, a smallest positive integer n such that the nth power of A equals 0. Okay, our aim is to show that A is 0. Now you can, if you want, proceed by supposing that A is non-zero. However, we will do something slightly different, which will ultimately lead us to A being 0. Suppose that this positive integer n is greater than 1. Then from this equation and those rules of exponents that we were mentioning back then, we get this. Okay, and we have been able to write this product in place of this because n minus 1 is a positive integer, and that is why this power in particular makes sense. If n minus 1 is negative, then in a general ring the power may not make sense because that power may not be an invertible element or a unit in the ring. But now we don't have those problems, because n minus 1 is positive, and so we can write like this. Now note that n has been considered to be the smallest positive integer for which this power is 0. Now n minus 1, because of this inequality, is again a positive integer, but it is less than n. So the minimal nature of n will not allow this power to be 0. The minimal nature of n implies that this power is not equal to 0, since D is an integral domain. So in an integral domain, the product of two elements is 0, one of which is non-zero. So we must have the other equal to 0, because we do not have non-zero zero divisors in an integral domain. We have this equal to 0. But now Okay, so actually what have we got? That we should interpret that properly. We have got something, and you may be tempted to write, okay, so a is equal to 0, and we have proved that a is 0, but no. Remember that whatever we have shown here comes from a supposition, and what that supposition is, it is that this n, which has been considered to be the smallest positive integer for which this equation is true, is greater than 1. However, here then we have found that an even smaller power of a is 0. So actually this is a contradiction, since n is the smallest, although we can see clearly what is being contradicted, but it does not hurt to again write that down. Positive, since n is the smallest positive integer for which this is equal to 0, n is greater than 1, and this also has been found to be 0, we have a contradiction. So our supposition is wrong. That is the correct conclusion. This thing is wrong. We cannot suppose this. So that means we are left with the only possibility that n has to be equal to 1. And consequently, a equal to a to the power 1, which is equal to a to the power n, is equal to 0. So that's what we wanted to show, that a is, we considered a to be any nilpotent element, it has turned out to be 0. So 0 is the only nilpotent element. So you can end the solution here. Next. Now here we see another type of element, a ring element A is said to be idempotent, is called if a square equals a. Prove that the only idempotents of an integral domain in an integral domain are 0 and 1. 0 and 1. Clearly 0 and 1 are actually idempotents. Okay, we need to mention that also. You see, there is a very subtle thing which many people would not notice here. Let me just complete the solution, then I will discuss about it. It may seem something trivial, but it has to be mentioned nevertheless. Clearly 0 and 1 are idempotents. Idempotent, this word is used both as a noun as well as an adjective. Since 0 square is 0 and 1 square is 1. That 1 square is 1 comes directly from the definition of the unity 1, and 0 square is 0, that comes from the elementary ring properties, that you multiply any ring element with 0, you get 0. Now let A be any. We did not even mention that we are in an integral domain, but let's just assume that that is there in the background. Okay, that assumption that whatever we are writing in this solution, we are doing it in an integral domain. So let A be any idempotent. In fact, let us just mention that also, in an integral domain. Then by the definition of idempotent elements, A square is equal to A, and hence A times A minus 1 equals, if you do the multiplication, you get A square minus A, this is equal to 0. This implies, because we are in an integral domain, that A is 0 or A minus 1 is 0. i.e. A is 0 or A is 1. Okay, now that thing that I was talking about just now, that subtle thing, is that many people will start the solution here and end here. There is no problem with that, but only a simple thing is there. What do you show if you just simply write this much? You just show that if any idempotent element is considered, then it has to be equal to 0 and 1. That actually does not prove that 0 and 1 are in fact themselves idempotent elements. They have to be mentioned separately, and I am saying mentioned because this thing is almost trivial. Okay, but nevertheless it has to be mentioned. So here you complete the solution. So 0 and 1 are of course idempotent, but now in an integral domain they are the only idempotent elements. Next, and this one is computational. Let A and B be idempotents in a commutative ring. in a commutative ring. Show that each of the following is also an idempotent. So a number of elements are given in terms of A and B. These elements A, B, then A minus B, then A plus B minus AB, and one more A plus B minus 2AB. So in with each of these elements, what we have to do, we have to just verify the condition for idempotence. Take the squares of each one of them and see whether that equals the element itself. So we go through the calculations one by one. Keeping in mind that A and B themselves are idempotent and we are in a commutative ring, because the commutativity will have to be used. In the beginning itself, here itself, in the very first step, this equals A square B square, because we are in a commutative ring. And now the fact that A and B are both idempotent implies that A square is A and B square is B. So AB whole squared equals AB. So AB is idempotent. But we continue, we will finally conclude. This is A minus B times A minus B. Write like this so that we don't make mistake while expanding this. We just simply multiply it, the terms out. A square minus A square minus AB. Actually it is A times minus B, but because we are in a ring, so in a ring we have all those properties we already have, that A times minus B is minus of AB. Then minus BA. Minus minus we get plus B square. Okay. Okay, so what is it that we have got here? Have I written these elements correctly? Oh no, see, I made a mistake. This is not A minus B, this is A minus AB. That's what I was thinking, because it's not coming. Then this entire thing will change. Okay, so now instead of cluttering the space like this, let me continue from there. Again, A square minus A square B. Minus ABA. Let's just first write ABA plus AB whole square. This equals, because A is idempotent, so A square equals A. because we are in a commutative ring, so ABA equals A square B. And see, the previous calculation already gives us AB whole square equal to AB. So here we can directly write AB. So that gives us A minus AB minus, again use the fact that A is idempotent, and you get this. So ultimately we started with A minus AB and we are getting back A minus AB. So A minus AB is also idempotent. Next, A plus B minus AB square, this is equal to A plus B minus AB times A plus, I should perhaps not use this type of symbols, A plus B minus AB. Just simply write this and then followed by this. So first we multiply all these terms by A from the left side. That side should also be maintained, although we are given that the ring is commutative, but in the beginning we do not assume commutativity. A square plus AB minus A square B. Then we do that with B plus, and because we do that with B from the left side, so we write BA plus B square minus BAB. Then we do that with minus AB. So minus ABA minus A B square plus AB whole square. Now we carefully do all the things that we need to do after this. In place of A square we will have simply A, AB will stay as such, minus A square B becomes AB, plus in place of BA we can write AB because commutativity, B square is B. Now we are at once going to write AB because we have AB square and B square is B, so minus AB. Here also we actually have A square B, but that is equal to AB. This one is AB, plus finally this one is also AB. So how many ABs we have? These two cancel out, AB minus AB, then AB minus AB, and also AB minus AB, so a single minus AB survives. And of course we also have A and B, so A plus B minus AB. So that's what we started with, and we are finishing with that. And finally we have this thing. A plus B minus 2AB. A square plus AB minus 2A square B plus BA plus B square minus 2BAB minus 2ABA minus 2AB square plus 4AB whole square. Now keep in mind that this minus 2ab has its own meaning, right? Do not think of it like this. Among the many ways of interpreting minus 2ab, if a and b are real numbers and we are in the system of real numbers or the system of complex numbers, this is one way. Now, I ask you to not interpret this term like this because we are in a commutative ring, but the ring may not have a unity, that is 1. It may not have a 1. So, this thing may not actually be, in a ring with no unity, this of course is meaningless. Instead, minus 2ab should be interpreted like this: minus ab, minus ab. Now with that interpretation, actually we carried out this calculation. So according to that interpretation, 4ab square is 4 copies of ab square taken together, and we are considering their sum. So if you want, you can write these expressions like this also and then carry out the computation. Ultimately you will see that you end up with this. Okay, now using commutativity, idempotence of a and b and everything, we ultimately have a plus ab minus 2ab plus, in place of ba we can write ab, plus b minus 2ab square, but that becomes ab, minus 2a square b, that also becomes ab, minus 2ab square becomes ab, and this of course becomes ab. Okay, so ultimately what do we have? ab, ab and minus 2ab, they cancel out, so this part is gone. Minus 2ab plus 4ab, they give us 0, so we are left with a, b and minus 2ab. So that's just it. So let us properly conclude the solution also. Hence, ab, a minus ab, a plus b minus ab, and a plus b minus 2ab are also idempotent. And let us solve one more. Show that the ring of integers modulo n, where n is a positive integer, has a non-zero nilpotent element if and only if this is an equivalent condition n is divisible by the square of some prime number. Okay, so let's see what we can do for this one. This has a non-zero nilpotent element if and only if the modulus n is divisible by the square of some prime. Now I don't remember whether this kind of rings have been considered only when n is greater than 1, or the case n equal to 1 has also been considered. So to take into account everything, I am going to assume also the case n equal to 1. So it may look silly that I am considering the case n equal to 1, specifically if in the text already said in this the rings have been considered only for n greater than 1. If that is the case, please ignore this first part. When n is equal to 1, n is not divisible by the square of any prime. In fact, n is not divisible by any prime itself. Also, in this case, this just has the single element 0, right? So no question of having non-zero nilpotent element. So anyway, the statement is true in this case. So this case is over. So we now assume n to be greater than 1. First, let there exist a prime P such that its square divides n. So we are assuming that one first, that condition. Now what we have to show is that there is at least one non-zero nilpotent element in Zn. So we have to somehow use this condition. Then if p square divides n, then n is equal to kp square for some positive integer k. Now consider the element Kp belonging to this. Okay, in the ring Zn or Zn, what do we have? What are its elements? Its elements are all the non-negative integers strictly less than n. Is Kp such an integer? Kp is of course non-negative. In fact, it is positive because p being a prime is a positive integer and k is also a positive integer. So Kp is greater than 0. Whether Kp is less than n? Yes, it is, because when you multiply another p with Kp, then only you get n. So that means Kp is naturally less than n, and that is also because p itself is greater than 1. So that is why we have the element Kp in Zn. Now if we suppose that in Zn Kp is equal to 0, it is very important to write in Zn, since otherwise Kp actually is never equal to 0. I mean, as integers these two things are never equal. We have just now said that Kp is greater than 0, but in the ring Zn, when you interpret it as an element of Zn, then Kp becoming 0 has a different meaning. It's not literally that Kp is 0, but rather that n divides the integer Kp. Then n divides Kp, but this implies, now what is n? N is Kp square, so Kp square divides Kp, that is p divides 1. If you turn this divisibility relation into an equation and then argue, you will get again another such divisibility relation, which is impossible. So that means Kp is not equal to 0. Thus, in Zn, Kp is a non-zero element. We now want to show that Kp actually is a nilpotent element, and that's how we will have a non-zero nilpotent element. Now, so the power of Kp, we are going to try to show that equals 0 is the smallest non-trivial power Kp square. Keep in mind that our ring, this modular ring, is a commutative ring. So Kp square is, we can just simply write it as, okay, so we have considered Kp, fine. So this gives us Kp square, or we can write like this also, K times Kp square. Okay, Kp whole square is K times Kp square, but we already know that Kp square equals n, so this is K times n, and in the ring Zn, Kn is 0 because it's divisible by n in this. So when we do this type of calculations, we always never fail to write in Zn, and we are having to write these things because we are considering the elements in these modular rings to themselves be integers. Strictly speaking, they are not, they are congruence classes. But let's not complicate matters further and proceed just like this. So what we have now? We have found a non-zero element Kp whose square equals 0. So that means it's a non-zero nilpotent element. Thus, so that means if our modulus n is divisible by the square of a prime, then Zn has a non-zero nilpotent element. Now we prove the converse. That is, if Zn has such an element, then n must be divisible by the square of a prime. However, we will not prove this implication itself, but rather its contrapositive. That is, if n is not divisible by the square of a prime, then there is no non-zero nilpotent element in Zn. That's what we will prove. Okay, so now conversely, we assume that n is not divisible by the square of any prime. So the case n equal to 1 actually falls under this. However, that we have left behind, and we are done with that. So that is why our n is now greater than 1, and this is our assumption. Since n is greater than 1, we have n equal to p1, p2, etc., pr for some distinct primes Now, what is happening here? You see, because n is greater than 1 by the fundamental theorem of arithmetic from number theory, n has a prime factorization. Now, our assumption that n is not divisible by the square of any prime implies that in that factorization, distinct primes will appear in their first powers. That is, no squares or cubes or anything, because if you have such higher powers, then the corresponding say if you have p2 to the power n, where n is at least 2, then p2 square will divide n, which is what we are assuming is not true. Okay, so now our aim is to prove that under these hypotheses, our Zn does not have a non-zero nilpotent element. We will now prove that by contradiction, supposing that there is such an element and arriving at a contradiction. Now suppose this type of numbers, integers whose prime factorizations have just distinct primes with their first powers, they have a name, they are called square free numbers. that is, they are not divisible by squares of any prime. Now suppose there exists a nilpotent element A not equal to 0 in set n or Cn, then some power of A equals 0 for some, I hope I have not used m anywhere here, no, for some positive integer n. Okay. Now a to the power m, it being 0, is happening in Zn, so it has that interpretation. Okay, since this is equal to 0 in the modular ring Zn, we have n dividing the integer a to the power m. That's what this actually means. This implies because n looks like this, so each pi now would divide a to the power m, because each pi divides n and n divides a to the power n. So this implies pi divides a to the power m for each I varying from 1 through r, since the pi's are prime. So we know from a well-known property of primes that if this happens, then pi has to divide a. And the property that we are using here is of course that one which states that if a prime divides a product of some integers, then it has to divide at least one of them. For each I lying between 1 and r. Now because the pi's are distinct primes, so they are pairwise relatively prime. That means if you take any two distinct pi's from here, then their greatest common divisor is 1. Since, let me continue from this side. We can write like this: GCD of Pi and Pj is equal to 1 for n are equal to r it follows that their product, which is n, divides our A. And this is again one of the divisibility results. It is like this. To recall what we have done here. We can, what I'm trying to say is this. You see, 2 and 3 are 2 primes, right? And their product, they individually divide 6. Each one of them divides 6. Now, because they are relatively prime, so their product also divides 6. This, however, is not necessarily true if they are not relatively prime. Now, the example that we can give here of that fact where things go wrong may be considered to be this. Eight and 4, both of them divide 24, because 8 times 3 is 24 and 4 times 6 is 24, but they are not, of course, relatively prime. The divisors 8 and 4. This in fact is 4 and it is not 1, and the conclusion also fails. This does not divide 24. So it's not like this situation. If the GCD is 1, then of course it will divide the thing that is already being divided individually by these divisors. And in fact, this is greater than 24. Okay, so you know what we have done here, not just with 2 primes, but with this arbitrary R number of primes. But now you see what we have, where we are right now. We have proved that N divides A. Thus, in our modular ring, A is equal to 0, and this is a contradiction to this. Which is a contradiction, and that contradiction stems from this supposition that there exists a non-zero nilpotent element in Cn. So our last supposition is wrong. That is, there is no non-zero nilpotent element in Cn. You complete that part. So I am ending the solution here itself. So in the next video, where this will again be taken up, we are going to continue with exercise 21 and so on. So with that, I end this video. If you want to comment something on these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And tomorrow we are going to again go back to real analysis, specifically infinite series. So that's just it. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.